We'll proceed again in proving the vector field path independence, what we are trying to do. Probably we will able to finish the proving the path independence in vector field. Vector field that is path independent. So that is the concept that we are pursuing for last two sessions, that can be proved that our vector is path independent. Vector field is path independent. What is path independence is vector field? What we have talked till now. Okay, so if this is the kind of consider this is x-axis, this is x-axis, and there is a 2 point on x-axis, A and B. There are 2 points on x-axis, and that is A and B, and there is a vector field like this. Vector field equation is capital F. Capital F is a vector field equal to F1I plus F2J, where F1 and F2 are component of vector field capital F. If there is a capital F vector field, then its component F1I plus F2J. Now F1 is a function over x and y, and F2 is function over x and y. It can be like xi plus x plus yj, or x plus yi plus x into yj, or xi plus yj, or yi plus xj, whatever. First component is function over x and y. Second component is function over x and y. If I deduce this kind of vector, then this is called vector field. If that is the case, and consider this is the origin and this is our vector field, has some equation, and it goes from here till here. If I keep changing x and y, vector field goes from here to here. Whatever I see in this arena, this comes in a vector field. So something like, if I have a magnet, if I keep two magnets, then there is a magnetic field that starts from one magnet to another magnet. So whatever comes in this arena, it's called magnetic field. Similarly, if I have a vector field, whatever comes in this arena, if I have a algebraic vector and it's changing from here to here, whatever comes in this arena is called vector field. Vector field can be force field, velocity field, it can be magnetic field, it can be electromagnetic field, anything. Vector field means a vector which is algebraic in nature. So it can produce so many static vector like 2i plus 3j static vector, so many static vector, if I keep changing x and y independent value. Now, what is path independence? Consider our vector is a force vector. If our vector is a force vector, then if this consider this is a vector field. Consider this is a vector field. If this is the vector field, and consider this is a vector field, what is the work done by this force vector field? This is a force vector field from point A to point B. Then F cos theta, then whatever comes as F cos theta into this distance. That is the work done from here to here. Or vector, if force vector field F dot dr vector. I'm not saying, I have repeatedly said this, I'm not saying vector field F dot vector dot product with R vector, because R is algebraic, vector field F is algebraic. If both are algebraic, then it comes in a calculus fashion. Then vector field F dot dr vector field F dot R vector, that is true for the work done if it is a static vector. Vector field F is 2i plus 3j along the direction, that is 5i plus 6j. If that is the case, then do the dot product and compute the magnitude. Okay, do the dot product and compute the magnitude and set a distance, that is the work done by the force along a distance. Similarly, if vector field is, vector is a static vector and distance we are trying, like vector is 2i plus 3j, 2i plus 3j. I have to move an item in x along x-axis, that is I vector, from origin to 4. What is the work done? 2i plus 3j dot I. That will come as 2 only. So force along x-axis is 2. 4 distance, 8 is the work done. 8 joule is the work done. But if vector is vector field x, y, I plus y, j, and this direction is the direction we are talking about in which the item would move, that is also a kind of algebraic vector, xi plus a square root of a square minus x square j. That is the path, means that is semicircular. We are trying to find if force is x plus yi plus xyj, that is the force field, and along the direction, that is circular direction, that is xi plus the square root of a square minus x square j. That is the case, then how much is the work done by that vector from a point A to point B along the circle? Then integration A to B vector field capital F vector dot, now it won't be R vector, it will be dr vector, because calculus will come into the picture when it is algebra. So because every moment in the circle, xy is changing. If xy is changing, the circular vector is also changing, and force vector at here at point A, force vector is like this. But as per the equation, force vector may also change if I go point by point along the circle. If that is the case, if it is 2i plus 3j, then force vector is everywhere, it is same direction. But if it is algebraic vector, vector field, force vector is also changing its direction and magnitude both along the curve of the circle. If that much variation is there, then it is vector field f dot dr vector, where r is the path along which we are calculating the force into displacement. This is also called line integral. Line integral means force vector dot dr, r vector, r is a line, force vector dot dr vector. So it is also called line integral. Or if it is a line integral, that capital F, that is vector field, need not be force vector. It can be any velocity vector, magnetic field, electromagnetic field, earth gravitational pull, whatever it is. Capital F dot dr vector. So this is also called line integral. Capital F means not as a force vector, it is a vector field. It can be force vector. If it is a force vector, then line integral leads to work done. Now idea is, can we prove that our line integral is path independent? Path independent in the sense that if I take a circle and from point A to point B, the way I am talking, I keep one small iron here, and the force vector is a magnetic force. Then this iron will, if it is here, then slowly it will come toward the magnet. So from here, slowly the iron will move along the path and it will come here. Consider this is A and this is B. Then how much is the work done by the magnetic field from, if if the iron is moving from here to here? That is the magnetic force field, that is capital F dot dr vector, integration from A to B, where capital F is the magnetic force, that we have to find out what is the equation of the magnetic force, dot dr vector. R vector is the circle, that is xi plus yj. Y is the square root of a square minus x square, where a is the circle. So it comes as f vector, capital F vector dot d of xi plus square root of a square minus x square j. That will come as dxi plus minus xy square root of a square minus x square dyj. And whatever vector field f is, then I have to do dot product Then I have to do integration from A to B. Path independence means this integration, whatever I am getting, this will be again an algebraic function. Capital F, that is the vector field, dot d of the r vector, that is the path vector, that whole is line integral. Whatever I get back from this integration is an algebraic function only. If it is an algebraic function, that algebraic function is called potential function. It is denoted by small f. Potential function, small f. If it is small f, then what is small f? Then integration is from a to b. If full integration is small f, then fb minus fa is the end result of the work done if capital F is a force vector. Okay, so capital F vector dot dr vector, whatever comes as integration, consider this is an algebraic equation small f. Limit is from a to b, small f limit from a to b, means fb function over b, point b, minus fa small f bracket curly bracket, and then b bracket close minus small f bracket a bracket close, fb minus fa. If it is path independent, then r vector I had taken along the circle. If I take along a straight line, I am worried about point A to point B, point A to point B. Point A and point B can be connected through a straight line also. If I take equation of a straight line, consider a straight line is x plus y equal to 1, y equal to 1 minus x. If I place this in dr vector, then whatever integration I am getting, that will come as again fb minus fa. If fb minus fa, the end result, I'm not saying f will be same. If end result fb minus fa is same as what we received in through the circle, then vector field is called path independent. Path independent means net result what we get at the end fb minus fa through potential function small f, that is only dependent upon point B and point A and the vector field, not on the r vector. If for line from point A to B, if its connection is through a straight line, point A to B, if connection is through a circle, point A to B, if connection is through parabola, point A to B, if connection is through a staircase, point A to B, if connection is through some another equation, if the net line, if I get a potential function of small f, then then fb minus fa is same for all the path, then vector field is called path independent. Path independent means net work done is only dependent upon the vector field and the point A and point B, not what is connecting point A and point B. Like we gave example that if I keep an item here and drop it and this place, what is the work done by the gravitational pull? Gravitational pulled it, right? Earth gravity. What is the work done by the earth gravity? Or if I make a shape like this and then I place this item here and this item is passing like this in a circular path, same point A to point B, what is the work done by the earth gravitational force pull? Same thing. Because the force, earth gravitational force is path independent. Path independent means work done from point A to point B, whatever the net work done is same. Either you drop it like this or you take a circular path and just leave it like a pipe. Take a pipe and leave the ball. Ball will go like this. Or do whatever. You drop the ball on a staircase and through staircase it will come from point A to point B, whatever. The work done by the earth gravitational force is same. It is dependent upon the two end point only. So net work done is dependent upon the gravitational force and two end points. That is the case. If that is the case, then gravitational force is called path independent. How I can prove that the vector field is path independent? That comes in question. If that is true, vector field is path independent. This proves that capital F dot dr vector equal to potential function f. If the potential function f limit from A to B means FB minus FA, whatever is FB minus FA, if FB minus FA, small f, is only dependent upon capital F, that is vector field F dot dr vector equal to potential function F, limit A to B, FB minus FA, it results in some value. If FB minus FA, this whole thing is only dependent upon vector field F, not on the R vector, then vector field F is called path independent, because net result is only dependent upon the vector field F and point B and A. Small f FB minus FA is only dependent upon the vector field F. Vector field F vector dot dr vector is the line integral from integration from A to B is work done if vector field F is force vector equal to a algebraic function that is called potential function small f. Small f limit A to B, FB minus FA. If FB minus FA is only dependent upon the vector field F, not on the R vector, then net result what we are getting, it is called only dependent upon the vector field and point A and B, not on the line. Then the vector field F is called path independent. How we can prove it? Same way we'll proceed now. Now I have a potential function f, that is algebraic equation fb minus fa, fb minus fa. Okay, fb minus fa equal to integration from a to b and then derivative of f dr vector. Dr. Is it difficult? Okay. So consider consider a xy plane. This is xy plane and it is kept like this, and this is x-axis, this is x-axis, and this is y-axis. If this this is x-axis and this is y-axis, this is y-axis and this is x-axis. Consider this is I vector, I unit vector, and this is j unit vector. Consider there is another vector called r vector somewhere in the xy plane, r vector, whose one point is a and another point is b, that is x1 y1 and x2 y2. If this is x-axis, then one point is x1 0, y is 0, x2 0. If I take on y-axis, then one point is 0, 0 y1, another point is 0 y2. But if I take any r vector, then one point is a and one point is b, then a is x1 y1, a2 is x2 y2. This is r vector. Now I am trying to calculate, I have any algebraic function f, any algebraic f is small f, any algebraic function f, fb minus fa. What is fb minus fa? That is nothing but integration from a to b and derivative of f, integration of derivative of f dr. R is this line, dr, any small distance on this line, dr, integration from a to b, derivative of f dr. Simple, right? Consider single dimension. I believe it will be more clear. Consider single dimension. This is x-axis, this is y-axis. I have any algebraic function fx, function over x. Now this is point A and this is point B. What is fb minus fa? What is fx? Fx is, consider fx is x square plus sin x. This is for example I give. X square plus sin x. Fx is function over x is x square plus sin x. What is fb? B square minus, b is any point on x-axis, b square plus sin b minus fb minus fa, b square plus sin b minus, and then a square minus sine a, b square minus sine b minus a square minus sine a. That is fb minus fa. So fb minus fa equal to integration from a to b derivative of f dx, derivative of f along x-axis, because there is only one x-axis line is there. Derivative of f dx is nothing but f1. Derivative of f means df by dx into dx, that is f1. And limit is a to b fb minus fa. So fb minus fa equal to integration from a to b derivative of f dx. Now in 3D we talked about r vector, right? In 3D this is x-axis, this is y-axis. Okay, in 3D this is x-axis and this is y-axis, and this is xy plane. If this is xy plane, consider this is any r vector. Then there are 2 points a and b. A is x1 y1, b is x2 y2. Now, there is any algebraic function, that is fx comma y, function over x comma y. So fx comma y, or if I say fb minus fa, or fx2 y2 minus fx1 y1, if there are 2 points. So there is r vector point, there is 2 points, one a and one b. There is a function fxy, that if this is xy plane, then fxy correspond to z axis. So fb minus fa, same thing what we did in 2D. Now it is 3D. There fb minus fa was integration from a to b derivative of f dx. Here again fb minus fa, where function is on independent variable x and y, fxy. It is not fx, fxy. Now same fb minus fa, where b and a are in x and y, not only x. So fb minus fa equal to integration from a to b derivative of f dr, because we are taking r direct, dr. If that is the case, then we are trying to calculate derivative of f along vector r. This is called directional derivative along vector r. That is, means this becomes this much in 3D. 3D is not that straightforward. 2D and 3D probably complexity is very high, not one time more, very high. Okay, see how big your earth is, that is 2D. 2D means it's a surface, right? How big your earth is. If you go to 3D, then there is no limitation. 2D, there is a limitation. If you go in 2D on the earth, you will come back to the same location, it is a circle. So it is 2D only. But if you go in 3D, then there is no limit. 3D is very vast. But anyway, now if I am saying fb minus fa equal to integration from a to b, and then derivative of f dr, because along the point a and b is along r line a to b. Now if I am saying derivative of f along r, then r axis, then it is nothing but directional derivative along vector r. Directional derivative along any vector r is gradient of f dot unit vector of r. This is, we have many times we have proved it. The directional derivative of any algebraic function fxy along r vector is gradient of fxy dot with unit vector along r direction. So consider that unit vector is u. So it is now gradient of f, that is the vector, gradient of f dot u unit vector dr. If u unit vector I transfer inside dr, then r becomes r vector, because unit vector is along r axis only. So net integration, that is fa minus fb equal to integration a to b, integration a to b, and then gradient vector of f dot dr vector. What you are getting here? Earlier I said that vector field F, capital F dot dr vector A to B equal to FB minus FA, where F is potential function, small f, algebraic function. Now I am saying from A to B, gradient of F, that is the potential function, gradient vector of F dot dr vector equal to gradient potential function, small f, FB minus FA. Isn't it same thing? Only thing difference is there it was vector field F, capital F, that is replaced by gradient of potential function, small f, gradient vector. But if that is the case, that vector field F, if I replace it with gradient of potential function F, then it becomes, the net result becomes FB minus FA1. Simple, right? If I say what is the work done by a force vector field capital F along any direction, that is r vector, then capital F vector dot dr vector from A to B, okay, that results in a potential function, small f, limit A to B, FB minus FA, FB minus FA. Okay, now 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 consider that I am replacing, if I replace force field F, capital F, with gradient of potential function F, then the result what I am getting, F is only dependent upon the gradient of F. Gradient of, consider there is an algebraic equation, small f, gradient vector of small f dot dr vector from A to B is equal to small fb minus small fa. The right hand side, what we are saying, a small fb minus a small fa is only dependent upon the gradient of f, because as per the calculus, this integration, the integration of derivative of f is nothing but f only, independent of what we are placing inside the dr. Gradient derivative of f, if I integrate, it becomes f1. If I integrate derivative of f, then it becomes f only. True, right? So if I say that gradient vector of f, gradient vector is nothing but derivative of f only in 3D. If it was 2D, x-axis and y-axis only, then that was simple derivative. So if I take simple derivative, that is in 2D to 3D, then simple derivative becomes gradient vector. In 3D, there is no derivative. If I have two independent component x and y, I have a function fxy, then I cannot say derivative of fxy. I'll say gradient vector of fxy, because two partial derivative will come into the picture. dfxy by dx, one derivative, dfxy by dy, one derivative. Altogether dfxy by dxi plus dfxy by dyj, it will turn up into gradient vector. So in 3D, there is nothing like simple derivative. In 3D, the derivative turns into gradient vector. So if I have integration of a gradient vector, that turns up into the pure potential function, fb minus fa. So if I say I have fb minus fa, and that equivalent of that is derivative of f, that is gradient of f dot dr vector. I don't care dr vector, because net integration is dependent upon, if I reverse gradient of f, then it becomes f. I mean, if I do integration of gradient of f, then it becomes f, a to b, fb minus fa. So if vector field f, capital F, is equivalent to gradient of f, then it is path independent. Making sense, right? So if I have a gradient of potential function, any algebraic function, gradient or derivative of any potential function, any algebraic function, for that derivative, if I integrate, it will result into the function itself. df by d whatever it is, df by d whatever it is, if I integrate, it will result back in f1. So if I am saying gradient of f, potential function f, means derivative of potential function f, if I integrate, it becomes f only. Limit is a to b, fb minus fa. This proves that if that is the case, then this integration is only dependent upon gradient of f, means on f. Makes sense, right? Now gradient of f dot dr vector a to b equal to fb minus fa. Now gradient of f I can replace with vector field capital F, then again it becomes fb minus fa. So if the vector field f is equivalent to gradient of potential function f, then it is path independent, because it is the net result is only dependent upon fb minus fa. fb minus fa. If I have a integration, if I have an integration from a to b, where the integration is of gradient of f dr vector, gradient of f dr vector, then it results in fb minus fa. R is gone. Can you see it? As per the calculus, if I say I have integration a to b of a gradient of f, f is a algebraic function, small f, also called potential function. What is the case? Case is I am calculating integration from a to b of integration happens to an algebraic function dr vector along the r. If it is dr vector, it is also called line integral along the r vector. I am calculating integration from a to b of an algebraic equation, that is gradient vector of any potential function f dot dr vector. What is the end result? End result is fb minus fa. fb minus fa. f, that is potential function for which there is a gradient of f, means net integration is only dependent upon gradient of f, not on the r, because and the end result is fb minus fa. There is no r in the result. If I am doing integration from a to b of a gradient of f, potential function f dot dr vector, then result comes as fb minus fa. Means result fb minus fa is only dependent upon gradient of f and limit a to b, not on the r vector. If this is the form, then this is line independent, because net result f, potential function f, is only dependent upon gradient of f, not on the r vector. Now left side equation, I can replace gradient of f, small f, with vector field capital F. If I replace like this, then net result what I get as potential function small f, fb minus fa, it is only dependent upon the vector field f. If that is the case, then vector field f has to be gradient of f. So if vector field capital F is gradient of potential function f, if that is the case, then it is line independent. Line independent in the sense that net result is fb minus fa. It is only dependent upon potential function at point B minus potential function at point A, not on the R. R is not coming at the end calculation. If vector field capital F is equal to gradient of the potential function F, or I can say, if I find any algebraic equation, if I have a vector field capital F, if I have a vector field capital F dot dr vector, and I find any potential algebraic function small f, for that algebraic function, if I calculate gradient vector and that becomes the vector field f, then vector field f is line independent. If we are not able to find it, then it is not line independent. If I have a vector field, I know a vector field like x plus y I, x plus yi is a vector field, x plus yi dr vector. R vector is now along any line connecting two point A and B. It can be circular, it can be straight line, whatever it is. But vector field is I plus x plus y I d of r vector. Okay. Now, can I find any potential function, any algebraic function for which if I calculate gradient vector, then that gradient vector become x plus y I? Not possible. Try any algebraic equation in the world, you try and calculate the gradient vector, it will never be x plus yi, not possible. If it is like that, then vector field capital F is path independent. Then r vector on which you are calculating the line integral, it is only dependent upon the one end and other end, not on the connecting line. It can be connecting line, can be straight line, circular line, or parabolic line, whatever it is. If I find any algebraic potential function of small f for which gradient vector is vector field capital F, because if happens like that, then it will come in a form like integration from a to b gradient of potential function of small f dot dr vector. If it comes in this form, then net result is only fb minus fa, potential function at b, potential function at a only. So the net result is only dependent upon the gradient of f, not on the r vector. If this comes into the picture, because it is proved through the calculus. Makes sense, right? So if vector field capital F, if vector field is capital F is equivalent to gradient of any algebraic function, potential function of small f, if that is the case, then vector field capital F is line independent, is considered as path independent, because it will come in the form of integration from a to b gradient of potential function f or algebraic function f dr vector, which results into fb minus fa, where r is not there, because this norm is path independent. If this norm is path independent, then gradient of f, if I replace with the capital F vector field and it is satisfies it, then the vector field capital F is called path independent. Now we take example as vector field F equal to x plus yi, x plus yi. Can I find any potential function, algebraic function small f, for which this would be the vector field? The gradient of any algebraic function, if I calculate d, consider small f, potential function, algebraic function is small f, df by dxi plus df by dyj. If this is the gradient of any potential function, if this gradient is same as x plus yi, then I can prove that x plus yi is path independent. You will not find a single algebraic function for which df by dxi plus df by dyj is x plus yi, x plus yi. Not possible. How we can try that? If I say that consider that vector field capital F, vector field is capital F equal to x plus y I, x plus y I, that is equal to x plus y I plus 0j, x plus y I plus 0j, that is equal to gradient of potential function f, means that is equal to df by dxi plus df by dyj, where f is small. So x plus yi plus 0j equal to small f df by dxi plus df by dyj. This proves that the potential function, then x plus y equal to df by dx, then f equal to x plus y dx, then x plus y dx equal to x plus y dx equal to x square plus yx. So potential function f is x square by 2 plus yx. Now plus any function of y. Potential function of small f equal to x square by 2 plus yx plus any function. Consider that function name is c. Any function over y. If I do df by dx, it will come back in x plus y. df by dx I vector plus df by dyj vector equal to x plus yi plus 0j. This is what we are saying. So f equal to x square by 2 plus xy plus any function of y only, because df by dx, if I do, then it has to be x plus y only, plus c of y. Now x square by 2 plus x into y plus c function c of y equal to f. Now do the partial derivative along y-axis. So df by dy equal to x square by 2 is gone, x plus y becomes x plus derivative of function cy. Now dy by dx, df by dy equal to 0, because there it is 0. So 0 equal to 0 equal to y, 0 equal to x plus derivative of function cy. So derivative of function cy equal to minus x. Then cy equal to x in minus x into y. But cy is function only of y, not any x should come into the picture. So not possible. So our vector field capital F dot dr vector cannot be represented as gradient of any algebraic function small f dot dr vector, because we could not find any vector, any algebraic function small f for which gradient vector is x plus y I plus 0j. So capital vector field F dot dr vector cannot be represented as gradient of any algebraic function dot dr vector. Not possible. If that is the case, then vector field capital F is not path independent. You can try with other vector fields also. We gave proof from other way. Here we tried from FB minus FA. From there we started our proof. We can go with the proof from this side also. This is our proof. So our proof is, if I want to prove that vector field is line independent, then line connecting point A and point B, this line I can represent in generic fashion. Then any point on the line is x comma y. Either it is a circular, it is a staircase, it is a parabolic, it is a straight line x comma y. Then position vector of x comma y is xi plus yj. Then vector field f dot dr vector, r vector I can substitute with xi plus yj, that is generic. So dxi plus yj is dxi plus dyj. dxi plus dyj. Then now vector field f can be represented as f1i plus f2j, because it's a vector, right? It has component. So capital F1i plus capital F2j. In earlier case, x plus y I plus 0j, x plus y was capital F1, whereas 0 was capital F2. If that is the case, then F1i plus F2j dot dxi plus dyj. Then F1 dx plus F2 dy is the net integration. Okay. If I am able to get this integration, then it will be algebraic function small f. Okay. Now if d capital, if f1 dx plus f2 dy equal to algebraic function f, then gradient of f will be vector field f. If vector field f has component f1 and f2, and with the path independence way, we came that our integration landed up into f1 dx plus f2 dy, and this results into vector into algebraic function small f, then gradient of a small f will be f1i plus f2j in reverse fashion. So we came to same situation, that if there is any function, algebraic function small f exists for which gradient vector is same as f1i plus f2j, then it is path independent. So we can prove from this side also, we can prove from this side also. So a vector field is path independent when we are able to find any potential function, algebraic function for which gradient vector is exactly equal to vector field. If we are able to find it, any potential function, then this vector field is called path independent. What drama it will show in path independent, that we will see. Why it will show curling, why it will not show curling, what is the curling and not curling dependent upon the path independence, that we will see.